I've always been fascinated by the almost superhuman abilities of elite table tennis players. I'm not very good at table tennis myself, but as a roboticist, I have often thought in the past how interesting it would be to build a table tennis robot, and to be able to do that was kind of a dream project for me. We developed Ace, the first physical AI system that can challenge elite-level human athletes at the physical sport, namely table tennis. My name is Peter Dürr. I am the director of Sony AI Zurich and lead engineer of Project Ace, one of our robotics projects at Sony AI. Table tennis is an amazing challenge, and if you look what the human athletes do, it's almost incredible. The ball flies over the table with speeds of 20, 25, sometimes 30 meters per second, and the table is only 2.7 meters long, so you can quickly understand that that leaves very little time to react. Moreover, when the top players hit the ball, they impart spin on it to arc the trajectory and make it more difficult for their opponent to react or to gain a tactical advantage. And the spins that we see can be above 150 revolutions per second. So that makes table tennis really, really interesting from a physics point of view, but also from the point of view of testing the limits of human reaction. So, in the history of AI research, games have often been used as benchmark problems because games allow us to compare the performance of our AI systems to that of human competitors. And in the past, we've seen that happen in board games like backgammon, chess, shogi, Go, and then also computer games like StarCraft and our own work on simulated racing in Gran Turismo. When you work on a problem in the virtual world, for example, a computer game like Gran Turismo, and your AI makes a mistake that leads to a crash, for example, the drivers are still safe behind their screens, and with the push of a button, they will be good as new. In recent years, we've seen some work taking to the real world, starting with a seminal work by Elia Kaufmann and his colleagues from the University of Zurich, who challenged expert drone racing pilots. And in the real world, like with a robot behind me, when that robot crashes into the table or into itself, can not only damage itself, but also potentially hurt someone on the other side of the table. So safety is a really big concern. And that was a key part of our contribution to enable a safe way to learn how to control this robot. The interesting thing about a problem like robot table tennis is that it's totally impossible to pre-program everything that could happen, right? So you cannot write code that controls this robot by hand. So what we did is we resorted to a technique from machine learning that's called reinforcement learning, which is really trial and error. So we put the robot in a simulation and we shoot table tennis balls at it. And at first it's moving randomly. Eventually it will hit the ball and maybe even hit it back to the other side of the table. And at that point, we have a signal that we can learn from. We end up with a controller that can play really, really well in simulation. And because our simulation is very close to the real physics of table tennis, we can then use that on our real robot to beat real human professional table tennis players. One of the key breakthroughs in our paper was to combine that learned component with optimization-based control system around it that lets us actually guarantee that the robot is never going to collide with either the table or itself. Like any robotic system, our Ace robot is really composed of three main components. On the one hand, we have the perception system that feeds into the control system, which then generates the command for the hardware. And you can see an earlier prototype of our robot arm here behind me. Our perception system, on the one hand, uses a number of conventional cameras running at 200 frames per second that are around the court, and they allow us to locate the ball in space, so we can triangulate the position of the ball in 3D. In addition, we also use something we call a gaze control system that's using an event-based camera, and that allows us to measure the spin of the ball as it's flying over the table. Spin is an essential element of the game of table tennis, as when the ball spins, that influences the trajectory of the ball while it's flying through the air, but also when it bounces on the table and then bounces on the opponent's racket. And when elite players hit the ball, they can reach spins of over 150 revolutions per second. So that's very hard to measure in real time. And one of the big breakthroughs of our system is that we found a method to measure the spin magnitude and also the spin axis in real time at very high accuracy. The resolution of the event camera in space is not that big, so we have to really zoom in on the ball, and to do that we built special optics that use two small mirrors that let us change the field of view of the camera very quickly and kind of follow the ball as it's flying over the table. And this allows us to then look at this logo, which in high-level table tennis games, we need to use balls that are ITTF certified and have a little logo printed on them. And by looking at the ball closely, we can see the logo as it's spinning around the ball. And this lets us identify the magnitude and axis of the spin. Having measured the position of the ball in 3D space and its spin, this feeds into the control system, which then computes the commands for the robot to move. And if you look at our system end to end, so from the ball flying in space to our robot generating a torque based on the observation of this movement, this takes us around 20 milliseconds, which is roughly 10 times faster than the reaction time of human table tennis players. When we started this project, we looked at off-the-shelf industrial robot arms, and we bought some of them, but we quickly realized that they wouldn't give us the reach or the speed we need to challenge professional level table tennis players. So we built our own arm that has 6 degrees of freedom to move the racket around, and then 2 additional degrees of freedom to move in space, which gives us enough reach and also enough speed to hit the ball at professional level. Yeah, when you want to evaluate the performance of a physical AI system that's built to beat table tennis players, the way to do that is to actually play games against table tennis players. There have been attempts before, but there were always some limitations like special equipment or rule changes that made it into quite different game from elite level table tennis. In our work, we paid a lot of attention to enable the human athletes to play on level playing field. So we went through the normal routine and let them warm up with a human in a friendly warm-up. We replicated the customary warm-up with your opponent before the game. We let the players use their own racket that they use in other competitions. We use certified competition balls. And we had licensed umpires who not only checked the racket of our robot, but then also officiated the games against our human opponents. And under these conditions, I think for the first time in history, we showed physical AI agent compete and actually outperform elite human players in a physical sport. I think like many sports fans watching a game of a player or team they support, I was also quite nervous because I really wanted our robot to win and I really didn't want it to make stupid mistakes. Of course, seeing the robot hit certain shots and win points against these incredible athletes made me feel very proud of my team and very happy to have been a part of it. Reinforcement learning with an optimization-based part lets our robot control run in the real world in situations that we haven't seen in simulation. A very interesting example of that happened in one of the early games where the ball bounced off the net and we really hadn't taken any effort to put that in our simulation, but the robot reacted flawlessly and returned the ball after it bounced from the net, and I do think we even won the point. And this is only possible because we have this combination of learned and optimization-based control. This robot is really one of the first examples of a robot that can interact with humans at the fastest timescales that we are able to interact with. We already see some of the potential of AI systems in the virtual world today. And when we give sensors, we give eyes and ears and touch to AI systems and let them manipulate things in the world, that's where there is a lot of potential and a lot of value to benefit society. And I'm really excited to see where the research community is going to take this.